Hello everyone, and welcome to our final video for the SMO Senior 2020. We will be going through the last 5 questions of the paper. In question 21, we are asked for the smallest positive integer that is greater than square root 7 plus square root 5 to the power of 4. The first instinct perhaps would be to use the binomial theorem to expand this, and hopefully the parts of it that are irrational are not too difficult to estimate. Well, let's see how that turns out. So use the binomial theorem. The square root of 7 plus the square root of 5 to the power of 4 is the square root of 7 to the power of 4 plus 4 times the square root of 7 cubed times the square root of 5 plus 6 times the square root of 7 squared times the square root of 5 squared plus 4 times the square root of 7 times the square root of 5 cubed plus the square root of 5 to the power of 4. Now if we simplify this, it turns out to be not too bad. Firstly, we have got 7 squared, which is 49. And then you have 4 times 7, which is 28. And then there's a leftover square root 5 and square root 7, which is square root of 35. And then the middle term is 6 times 7 times 5, which is 210. The fourth term is 4 times 5 times square root 35 again. So that is 20 square root 35. And the last term is 5 squared, which is 25. And so that means that if we combine all these together, 49 plus 25 plus 210, that part's okay. It is 284. And then we have plus 48 square root 35. So this is mildly annoying because it requires us to estimate square root 35 to a decent degree of accuracy if we want to find the smallest positive integer greater than this. We can't just estimate it is around 6, because if you have 48 times of the square root, then any error is going to be multiplied by 48. So if we have no means to estimate square root 35 to that degree of accuracy, what do? The simplest way to deal with this is actually quite clever, and that is to use the conjugate. Now remember, the conjugate of square root 7 plus square root 5 would be square root of 7 minus the square root of 5. We can't just multiply it to the number because that would change the value entirely. We also can't just add them together because that wouldn't really help. However, what we can do is we can also raise this to the power of 4. By raising it to the power of 4, the only difference between the first and the second expansion is the plus and the minus. As we know, if we were to expand this to the power of 4, it is going to be actually the same thing, except that the alternating terms would have a negative sign instead. Conveniently, we see that those terms with the negative signs are all those with the square roots. So, if we were to add them, the square roots will cancel out, and we would just get 2 times of the integer parts, which we know is 284, which is equal to 568. The last thing to ask is, how much have I changed it by adding this? Well, square root 7 is between square root 4 and square root 9, so it is 2 point something. And square root 5 is also 2 point something. In other words, the difference is something less than 1, and if we raise that to the 4th power, it is still something less than 1. So if it's less than 1, it means that by adding them together, the sum of these two is the same as rounding up the first expression. since we are just adding something less than 1 to make it into a whole number. Since the question is asking us to round it up, that means 568 is precisely our answer. Take note that this method works because the two numbers square root 7 and square root 5 are pretty close together. So before you try something like this, do check whether the two numbers are close enough that adding the conjugate power is not going to cause you to change the value by too much. Next up, question 22. Find the number of non-congruent right-angled triangles such that the length of all their sides are integers and that the hypotenuse has a length of 65 centimeters. Let's draw this. And I can't really draw it to any scale because we're supposed to count how many non-congruent ones there are, so obviously I'm just drawing one for show. The only thing that constrains it is Pythagoras' theorem. We are looking for a squared plus b squared equals to 65 squared, where a, b are integers. Now, a squared plus b squared equals to 65 squared. You might ask, then, how do we do this? Well, one way, which is a little bit unpleasant, but might be our only resort if we have not encountered such a question before, would be to just do a very slow listing method. By listing, perhaps the only thing we can do to make the listing less long of a list is to make b, assume b to be greater than a. That means that b squared would be more than half of this. And if we do a quick calculation, this would mean that b squared has to be at least 2112.5, and so b is at least 46. Now this is not really very exciting because it tells us that, oh no, I have to check b equals to 46, 47, 48, and so on until 64. But a slight consolation is that we can write it using a difference of squares. So a squared is 65 plus b, 65 minus b, and so for all these values of b, we just check whether the outcome is a square. Now this is still very unpleasant. So I'm not going to advise this method, but rather I'm mentioning this only as a practical approach, meaning that if we are at this problem and we have something like 20 minutes left and no other ideas what to do, something like this would take less than 20 minutes to work out. However, I'm sure we would want to do something better, so let's try to work out the intended approach to such a problem. Now, the intended approach requires us to know something about Pythagorean triples. Now, what are Pythagorean triples? They are integers a, b, c such that a squared plus b squared equals to c squared. Now, the most common ones that we know are 3, 4, 5 and 5, 12, 13. But certainly there are infinitely many of them. Now, I think this video is not the right time to prove that we only can generate Pythagorean triples in a certain way, but it is as good a time as any to tell you what that is for now. So how it works is that we can write A, B, and C in the following way. Now, A can be written as P squared minus Q squared, B can be written as 2PQ, and C can be written as P squared plus Q squared, where PQ themselves are positive integers. Now I have to add a caveat, which is that, remember, we can always scale up the lengths and still get a right angled triangle. For example, if we have 3, 4, 5, we can always scale it up to 30, 40, 50. So there can be a common factor which I'll call D. And we can place D as a common factor for A, B, and C. So D is a common factor. Once we know this, it will help us to check all the possible values of P, Q, and D, and that will in turn tell us the possible values of A and B. Since C is equal to 65. Let's write down the few possibilities. Now, it is possible that D is 1, and P squared plus Q squared is 65. P squared plus Q squared equals to 65 is immensely more pleasant than A squared plus B squared is 65 squared. So we can just list it out and it would tell you that P is 7, Q equals to 4, or P equals to 8, Q equals to 1. Now this would give us two possibilities. The first would be that A is equal to 33 and B equals to 56. In the second, A would be equal to 63 and B is equal to 16. Now there are a couple more, and those are easier to deal with. So if D is equal to 5 and P squared plus Q squared equals to 13, then the only case is P is 3, Q is 2. Substituting in, you realize that this is actually a 5, 12, 13 triangle, just scaled up by 5. So A is 25 and B is 60. Finally, and I'm fast running out of space, D can be 13 and P squared plus Q squared equal to 5. So P would be 2, Q would be 1, and this is actually a 3, 4, 5 triangle scaled up by 13. So A would be 39 and B 52. Obviously, D cannot be 65 itself because that would mean P is 1, Q is 0, and I'm going to have a degenerate triangle. So this would be all the 4 possibilities, and that tells us that there are 4 possible triangles with hypotenuse 65. So I will challenge you to think about why these are the only possible Pythagorean triples, but this is not such an easy exercise. So feel free to Google it or to search for some other videos that explain the reason why these describe all Pythagorean triples. Next up, question 23. This is a combinatorics problem. There are 6 couples, each comprising a husband and a wife. Find the number of ways to divide the 6 couples into 3 teams, such that each team has exactly 4 members and that the husband and the wife from the same couple are in different teams. Okay, so this is quite interesting because we can't really place them one by one due to the multitude of conditions to satisfy. So you need to make sure that every team has 4 members, and then there are 6 couples for all 6 couples, the husband and wife must be in different teams. Now, be very careful when you're doing any combinatorics problem to make sure that you don't overcount or undercount. Now, the first thing I'm going to do is to give the names to the teams A, B, and C, which are temporary names. Why I say they are temporary is because technically the teams are not named. So we will need to take note of this later when we are counting the different possibilities. Now, among the 6 couples, each couple essentially has a decision. They can either go A and B, A and C, or B and C, since they cannot be in the same team. Notice that there are 6 couples who have to make this decision. And the 6 couples making these decisions would end up giving each team exactly 4 members. So it's not too difficult to tell that the only way this happens is 2 couples split themselves into A and B, 2 couples split themselves into A and C, and 2 couples split themselves into B and C. Once that happens, we essentially guarantee that all the conditions are met. Now, let's go and count how many ways there are to do this. The first step is we need to decide which couple picks which configuration. Now there are 6 couples, so 6 choose 2 for the first configuration, and then there are 4 more, 4 choose 2 for the second configuration. This would be 15 times 6, so 90 ways to pick the configurations. Next, you need to make sure that the couples also can decide who goes into which team. So for example, if the first couple picks AB, does the husband go to A or the wife go to A? So the configurations can be set, but the next thing is, where do the husband and wife go? And the answer is that there are 2 choices for each couple, giving you 2 to the power of 6, which is 64. Lastly, before we want to multiply 90 and 64, there's also the overcount. Now the overcount comes from the fact that I named the teams A, B, and C when there weren't actually any team names. They are just 3 different teams. So the overcount comes from the fact that I've allocated the teams. So the team names give you 3 factorial ways of labeling the same configuration. So therefore, our answer is 90 times 64 divided by 3 factorial, which is 6, and this is 960. If we had not named the teams, this would be a little bit more difficult to describe, because we will need to say the same team as the other couple's husband, the same team as the other couple's wife, and that would be much more complicated and mistake prone. So we can bring in order temporarily, even though the question didn't ask you to consider the order of the teams. But after that, you have to divide back off whatever overcount you have inadvertently brought into the question. Next up, question 24. The digit sum of a number is the sum of its digits. Not a very surprising name. Now let A be the digit sum of 2020 to the power of 2021, and let B be the digit sum of A. Find the digit sum of B. Okay, I think I don't want to say digit sum so many times, so I'm going to name it. So I'll say let Dn be the digit sum of n. Now what we want is the digit sum of the digit sum of the digit sum of 2020 to the 2021. So that will be d of d of d of 2020 to the 2021. Now this seems at first to be quite impossible because 2020 to the 2021 has a lot of digits. Admittedly, the ones at the back are all 0, but even if we remove them, 222 to the power of 2021 doesn't seem any better than what we started with. And we're supposed to repeat the digit sum 3 times. How do we do that? Well, there are 2 important observations when we look at digit sum. Now the first one, remember that the digit sum is how we do the divisibility test for 9. You look for the sum of digits and then you find its remainder when divided by 9. That should be the same as the remainder when the original number is divided by 9. So that means that doing the digit sum, doing d of n, doesn't change the remainder when divided by 9. So for those of you who know modular arithmetic, I'm just saying that it preserves the value modulo 9. The second observation is even more obvious. I want to say that doing the digit sum shrinks it a lot. And that's important because if the digit sum doesn't shrink it a lot, we're starting with something really big. Shrinks n by a lot. So I'm going to do these 2 observations and combine them to figure out what is the answer. Now, first thing, I want to know what's the remainder when divided by 9. So that will give me at least some information on my final answer, because if I do it once and it doesn't change the remainder, then doing it 3 times will still not change the remainder. Now we know that 2020 gives you a remainder of 4. So if I want to find out what's the remainder, I can just find the pattern. So 2020 squared gives you 4 squared, and 4 squared is 16, so the remainder is 7. Now for 2020 cubed, you can do 7 times 4, which is 28, and the remainder is 1. And once we see a remainder of 1, then we know that it's going to repeat. And so, all the way to the 2021st power, what would the remainder be? Well, it repeats every 3 times. So 2021 divided by 3 gives you a remainder of 2, and so it would be the second term in the sequence. The remainder will be 7. So 2020 to the 2021 divided by 9 gives you a remainder of 7. So what does that tell us? Well, it could be your final answer is 7. Your final answer could be 7 plus 9, which is 16. It could be 16 plus 9, which is 25. There are still lots of possibilities. So the other thing which I need to know is just how much does this shrink n by? Well, let's look at this example here to show you how fast it shrinks. Now, first of all, a is the digit sum of 2020 to the 201. I can just ignore the 0 at the back because that doesn't contribute to the digit sum. And I'm going to use a really lousy estimate here. And my really lousy estimate I'm going to use is, I would say that this is less than 1000 to the power of 2021. Well, that's a truly horrendous estimate. But the purpose of me doing this is just to get an idea of how many digits to expect. So this would be 6063 digits. So if there are 6063 digits at most, then I have a very rough idea of the maximum possible value. It is at most 9 times 6063, which is 54,567. So this is a really rough estimate. Now let's take the digit sum again. B is the digit sum of A. Since A is now at most 54,567, the largest possible digit sum is 49999, which is 40. Finally, your outcome, which is the digit sum of B, is at most going to be the sum of two digits. 3 plus 9 is the maximum. So it can't be bigger than 12. Now, is it going to be 12? Of course not, because we also know that the remainder is 7. So we have a combination of two things. One is that the remainder is 7. The other is that it is at most 12. So we can only have one conclusion from here, and that one conclusion is that the answer is 7. Now the digit sum actually behaves like a logarithm of sorts, in that it does a sort of digit count, and that's the most that it can possibly give you. So even though you may start with something huge, just doing the digit sum 3 times can shrink it all the way down to just a 2-digit number or a 1-digit number. So the next time when you see a digit sum, take note of these two observations. Either it doesn't change the remainder when divided by 9, or that it shrinks it by a lot. And perhaps in examples like this problem, we use both. Last but not least, question 25. They give two examples of divisors of 1440. 40 is a product of 4 prime numbers, and 48 is a product of 5 prime numbers, and we are asked to find the sum of all the positive divisors of 1440 that are products of an odd number of prime numbers. The choice of 1440 is particularly nasty because 1440 has a lot of factors, and that makes it harder to just do this by listing or by observation. Now we have to start by factorizing 1440 because that's the only way we can know what sort of divisors I should look for. What I like to do when factoring is just to look for any obvious factors. So I write it as 10 times 144, which is 10 times 12 squared, and 10 is 2 times 5, 12 is 2 times 2 times 3 squared. So this is the fastest way I can try and factorize it. 2 to the power of 5 times 3 squared times 5. Okay, now that means that this has quite a lot of factors, and we can't afford to list them all out. How do the divisors look like? Now, divisors will look like 2 to the power of something times 3 to the power of something times 5 to the power of something, where we have the condition that a plus b plus c is odd, and of course it is a divisor. So a is at most 5, b is at most 2, and c is at most 1. So how do we then go about summing all of these? Well, we can actually split this into a few cases. And the reason why we want to split into cases is that it helps us a bit with our calculation. Now my cases that I split will be in order to make A plus B plus C odd. I don't think it's useful for me to split into A equals to 0, 1, 2, 3, 4, 5 because each of them will still not lend themselves to a quick computation. So my cases would be that A, B, C are odd, only A is odd, only B is odd, I should say only A is odd, only B is odd, or only C is odd. So there are 4 possible ways in which A plus B plus C can be odd. Now each of these give me some possible values of A, B and C. But any combination of A, B and C being odd is okay, right? Since it doesn't matter which odd numbers I look for. So here's how we can calculate the sum quickly. I'll just group it as 2 to the power of 1 plus 2 cubed plus 2 to the power of 5 multiplied by 3 to the power of 1 multiplied by 5 to the power of 1. That's the only way you can have A, B and C be odd. All of the 3 exponents are odd. So this actually includes 2 times 3 times 5, 2 cubed times 3 times 5 and 2 to the 5 times 3 times 5. Let's calculate this. It's 42 times 3 times 5, which is 630. Next, only A is odd. That means that A, the power on 2, can still be 1, 3 or 5. However, B is even means that it can be 0 or 2. And C is even means that it is only 0. So we can calculate this fairly easily again. It is 42 times 10 times 1, which is 420. And you see that if we were to expand this, it gets every combination of a power of 2, a power of 3, and a power of 5. We can repeat this a couple more times, and I'm going to elaborate a bit less since the pattern is similar. For the second one, only B is odd. So 21 times 3 times 1 is 63. And lastly, only C is odd. So A and B are both even. (21) times 10 times 5. Oh, this is the biggest one. Okay, and that's all. So we sum up all of these, and the total is 2,163. Perhaps you realize there weren't actually that many cases. The first one was 3 cases, then 6 cases, then 3 cases, then 6 cases. So in total there were 18 such devices. However, even just thinking of adding those 18 devices, you can see there are lots of ways in which we can go wrong. So as much as this is slightly frustrating perhaps, it is still better than listing out all the factors and adding them one by one. With that, we have come to the end of the SMO Senior 2020. Thank you for watching this series of videos, and do go back and look at earlier questions if you just came here. Please continue to look out for more videos like this when we go through SMO problems or other competitions around the world. So please do like this video and subscribe for more similar content in the future. Thank you very much, and see you guys again soon.